Ray tracing is great. It really does give you a good handle on what's going on, and if you don't have to measure it too carefully, then it's a good way to get a consistency check. If I have a lens like this and I know my focal point's here, and I put my object out here, I don't even have to really take my time to measure that too carefully. I can get kind of a general idea, right? I can do one of these and say, here's the other one. And I know that I should be making, I'm outside the focal length by a ways. I'm making an inverted image. Out here, it's a real image. And that's great. It doesn't help me to measure things unless I carefully measure these distances, but it gives me a good ballpark idea, which on something like a multiple choice test, like say the MCAT, that can be enough to get you to your right answer without having to do any math or any real measuring. It's just a ballpark quick sketch. But we also have a lens equation. And the lens equation looks like this. 1 over d object plus 1 over d image equals 1 over f. That's great. It gives us enough information to be able to solve for d image, which is generally what we're solving for. So if we want to solve that for d image, we can say 1 over d image equals 1 over f minus 1 over d object. We can plug in these values, solve for 1 over di, and then just flip our fraction. This equation is not the same as saying do plus di equals f, right? Those don't work, so don't do that. What we need then for this lens equation is some sign conventions. With a concave, with a convex lens, we had a focal point that was over here. With a concave lens, we had a focal point that was over here. So for a convex lens, we are going to say that our focal length is a positive number. For a concave lens, our focal length is a negative number. We can do a little bit more. Our object is always going to be over here on the left side. That's just the way we draw it. So our object distance is going to be positive. And that gives us enough to be able to solve. All we really need to worry about with this lens equation is making sure that we're plugging in the right values. I don't like to remember this one in terms of the minus sign. I think that actually sets us up for ambiguity with plugging in minuses and whatever you like. So I like to remember the equation this way. It's all pluses. It's really straightforward. Your distances are on the left, your f is on the right, not a big deal. When we do that, our d object is always going to be a positive number, and our focal length is positive for a convex lens, negative for a concave lens. There is a separate equation for mirrors, so this is the lens equation. For mirrors, we get an equation that looks like this. Now you might be looking at that and saying, but that's the exact same equation. And it is. The difference between these equations is whether I am looking at a lens or a mirror. We call it the lens equation, but if we're using this with a mirror, then, we can call it the mirror equation. So we need these same sign conventions. If you're ever unsure what you are doing with these are called sign conventions. So with a convex mirror, which is really just a circle, right? A sphere. Our focal point for this thing was in here. And with a concave mirror, our focal point was out here. This focal point is inside the mirror that's not made by actual light rays. So for a convex mirror, our focal length is negative and our object distance is positive. For a concave mirror, our focal length is positive and our object distance is positive. Those are our starting sign conventions. So I want to put these together into one kind of simple, have all the information in one location type of equation, or table rather. And it looks like this. I can go convex lens, concave lens, convex mirror, concave mirror. And let's go DO, F, and DI. So I've got the makings of a table. Here we go. Positive, 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 positive. That was easy. A convex lens, I get a positive focal length. A concave lens, I get a negative. And for mirrors, it's the opposite, appropriately enough. So a convex mirror gets a minus, concave mirror gets a plus. Now we're going to pull together some of these other things. For a convex lens, if I have D object greater than my focal length, then my D image will be positive. If I have D object equals focal length, I'm going to get infinity. It's not something I'm going to be able to solve, which tells me my image is formed infinitely far away. That's like my image not being formed. And if I have a D object is less than my focal length, I'm going to have a negative DI. For a concave lens, I'm going to have a D image that's negative always. Next, for a convex lens, I'm going to have a D image that's negative always. And for a concave, that's for a convex mirror. And for a concave mirror, I'm going to have the same situation. DO equals F and DO is less than F. I'm going to have the same situation as up here. Go positive, infinite, and negative. So what I'm looking at, a positive D image is going to be real, and it's going to be inverted. A negative D image is going to be virtual and upright. And all of this just plugs into my lens equation, or a mirror equation if it's a mirror that's in front of me. That's it. That's lenses and mirrors summarized and done mathematically.